All right. Good morning, everybody. Can you hear me? Can you see my screen?
Good morning, sir.
Morning, sir.
Yes, we can see the screen.
Morning, sir.
Okay, good morning. Thank you for your response. Hopefully, you're doing fine. All right, let's take a moment to scan your attendance and then we'll begin with our class today. All right, good morning, everybody, once again, and welcome back to our class today. Okay, so today we will continue from where we left off in the last class, right? But before that, like to wish everyone well. So today will be a day we complete topic 3. Actually, we want to complete topic 3 the last class, but I figured out that it's too much for you guys to take in one go. So then we have this class today. All right. So wherever you are, I really hope that you are doing fine. And to those of you who have, some of you did actually send me your difficulties on your laptop or on your device. Yes, I've got those emails as well, and I've also forwarded them to the person in charge. So um, if if you got hopefully like by in a short time they will get in touch with you. All right. So do let me know as we go on if you face any kind of difficulties, whether it's in your uh, studies or whether it's related or not. Like I will be here to help you if I can. All right, so to those of you who are new in the class, welcome to the class. And we are right now already in topic 3. Really hope that you can catch up with the rest of the class really quick. Okay, so I believe there are at least 3 or 4 new students who just managed to enroll this week. Okay, so let's get back to our class today. So this week, in the throughout last class, we have covered this topic, logic gates. And this is a relatively fun topic, relatively simple and easy topic because it's something that maybe you guys are already familiar with. Okay, we have covered simple things about Boolean, what's Boolean logic, and then we've also covered about block diagrams. How do you read logic gate block diagrams? Okay, what's the input, what's the output, and we've also covered 3 important elements in this topic, which is truth table, timing diagram, and Boolean expression. And we've done these 3 things. So these 3 things are the 3 elements that we can use to describe any logic gates. Okay, actually, not only can you describe any logic gates, you can describe any system. Okay, any digital system using these 3 elements. Okay, right. So we went through how we construct each one of these truth table, timing diagram, Boolean expression for the basic logic gates. So what are basic logic gates? So these are the basic logic gates: AND gate, you have OR gate, and then you have the NOT gate. So I believe we went into very detail on what's the symbol and everything. So if you're not yet familiar with this, I highly encourage you guys to watch back the class recording. And of course, after this class also, I will post a short video that will help you understand more. Okay, this is AND gate and OR gate. And we also did some exercise on a combination of gates. Okay, so this is a small system that I was talking about just now. So using a truth table, using a timing diagram, or using Boolean expression, we can actually describe the workings of this small system over here. Okay, so this is a very simple system. It only has 1 gate, 2, 3, 4, 5 gates. So in a real system, in a real world system, you might be dealing with thousands and thousands of gates. Okay, right. So, but the principle is still the same. You can still use Boolean expression. You can still use timing diagram, and you can still use what's the other one again? Timing diagram, Boolean expression, and truth table to describe the workings of this system. All right. So, and also I left you guys with one exercise for you to do at home. So hopefully you've done this exercise. Feel free to share the answer after the class in the comments or something, so that we all can help one another verify. So remember, as I said in the beginning of the class, like we are not competing with one another, because there's no such thing as ranking in this class, in my class at least. Right? That I don't rank people based on your performance in the class. I think everyone is equal in this class, okay? And we are all in the same boat. So you're not like competing against one another. So if you do have some kind of resource, like share it with the rest of the class so that everyone else can benefit, right? So in this one, in this exercise too, if you've gotten an answer and you're not too sure, or you want to share this answer, or you're sure already you want to share this answer for the rest of the class, I highly encourage you guys to do that. Okay, so not only will you help other people learn about this, but you will also help yourself learn solidify this knowledge again, right? Because when you teach it to someone, you'll get to learn it twice. Okay, so let's continue from where we left off. So today we are going to discuss advanced logic gates, and then we'll conclude this topic. So in the last class, we discussed basic logic gate that consists of AND gate, OR gate, and NOT gate. So let's talk about advanced logic gates. So what are advanced logic gates? So these are a few advanced logic gates. Advanced logic gates. So why do we say these are advanced logic gates? It's not advanced because they are complicated. They are equally simple. They're equally simple with this basic logic gates, as we have seen in the last class. It is called advanced logic gate because it can be built with simple basic logic gate. Okay, so can be built using simple logic gates. Okay. So these simple logic gates are AND gate, OR gate, and NOT gate. So using a combination of these three, AND gate, OR gate, NOT gate, we can build any one of these advanced logic gates. Okay, can build any one of this. So that's why these are known as advanced logic gates. So these are basic logic gates because they are the basic building block. Basic building block. Okay, you cannot break this into simpler gates anymore. Okay, but this one is a combination of the basic building blocks. All right, let's take a look at each one of these gates and how they work. Let's start with the NAND gate. Okay, some of you might have heard about the NAND gate, but a NAND gate is just a combination between an AND gate and a NOT gate. Okay, AND gate, and then you channel the output into the input of a NOT gate. That is all. And the way we draw it is like so. Okay, instead of drawing it like this gate, like this, two separate gates, so we can combine this into one simple gate, which is the NAND gate, and it's drawn like this. You can see that there are similarities over here. There's an AND gate over here structure, and then like the NOT gate is only represented with a bubble. So usually in digital logic design, if you have a bubble like this, it will mean it is a NOT gate. Okay, that's how we simplify a NOT gate as well in any schematic diagram. All right, so this NAND gate, yes, it is a hotcake because it is very popular. So it is very popular even in the computers that we use today, NAND gates. So there's a reason for this popularity. We'll go through this. All right, so the reason is because it is known as a universal gate. Okay, so here's another twist to this plot, right? Remember just now I said that using the basic logic gates, we can construct this NAND gate, we can construct this any other advanced gate. And it turns out that this NAND gate, using NAND gates, we can also construct any other gates. Okay, so I'll show you in the next topic, I think, on how we use NAND gate to construct any other gates, including the basic gates. Okay, so that's why this NAND gate is called a universal gate. So for now, just know that this is a universal gate. You can use this NAND gate to construct anything at all, like really. So that's why this is a very popular gate. Okay, so let's take a look at how it works. So it's simple enough, just like what we have covered in the last class. So it is just an AND gate, and then after the AND gate, you got a NOT gate in front. So what happens is that the Boolean expression is a Boolean expression of AND gate, which is the one below here, AND gate. A multiplied by B is a AND Boolean expression, right? And after that, you take a inversion on top of the results. Okay, so this is N, and then after that you invert the results of the N. That is the output X. Okay, this is the output X, and that is the Boolean expression. So just by looking at the Boolean expression, you can roughly know, okay, how the truth table might look like. So this is how the truth table will look like. And the output will be A multiplied by B, and then you invert the results. So over here, you have A is 0, B is 0. You multiply them together, you get 0. But then you invert the results and you get a 1. So that's how you get 1 over here. Same thing over here, 0 multiplied by 1, 0. Then you invert it, you get 1 and 1. And over here, 1 multiplied by 1, you get a 1. And then you invert it, then you end up with a 0. Okay, so that's how you get the truth table of a NAND gate. Right, same thing from the truth table. You can also draw the timing diagram. I am not going to go into like detail in the last like what we did in the last class. So I believe you have already familiarized yourself with how to draw a timing diagram. So if you're not, feel free to watch back our previous class lecture on this topic. So timing diagram of NAND gate. All right. So the NAND gate has got some more special characteristics that I want to cover today. So the NAND gate, so I want you to keep this in your mind for now, because we are going to use this knowledge in the next topic. So the NAND gate is equivalent operation to a negative OR gate. Okay, negative OR gate. So don't be bothered by this complicated table over here. It's not complicated at all. Let's take a look at this this diagram over here. So on the left over here, we have a NAND gate. So on the right over here, we've got something weird looking over here. So this is called a negative OR gate. Okay, it's called negative OR gate. So this is like it's not like a standard gate. So it's called a negative OR gate because like you have two NOT gates at the input of the OR gate. Okay, it's not like a standard gate. It's not something that you see very commonly, but you see that the operations of these two gates are equal. So they are equal in a sense. So remember in the last class how I talked about how do you know that one gate is equal to another gate in operation, or one system is equal to another system in operation? How do you know that? So the only way for you to know that is through by comparing the truth table, or by comparing the output of the truth table, that is one, or by comparing the Boolean expression or the timing diagram. Okay, so in this case, we are going to compare the truth table. So I've drawn the truth table for these two gates. On the left, I have the truth table for NAND gate, which is what we saw just now. Nothing fancy over here. But on the right, I've also gotten the truth table of negative OR gate. Okay, so for the sake of letting you understand how I got this truth table, let's just quickly do it. So I have A and I have B, and so I have 0, 0, 0, 1, 0, 1. Okay, So this is the truth table for negative OR gate. So how do I get this output? The output over here, we can see that you can redraw this gate to be like this, actually, if you want. Okay, if that helps you see much clearer on what is going on. This is A, this is B. So after going through this becomes A bar. After going through this becomes B bar. The output is A bar plus with B bar, like so. Okay, so this is not, okay, so A bar plus B bar. Okay, bear in mind, this is not the same as this, okay? It is different. Okay, that is a totally different thing. So don't be confused with that. Okay, so right here, what we are going to do is we are going to draw this A bar over here. Oh, I am sorry for my drawing. I don't have a ruler for this. Okay, A bar and B bar. And lastly, we have the output of A bar, B bar. This is the output. Okay, so this is our output, the output that we want. And let's just work through this. What is A bar? A bar is just an inversion of A. So I'm just gonna do that. Inversion of A. Okay, so A is 0, over here it becomes 1. A is 0, over here it becomes 1. A is 1, over here it becomes 0. A is 1, and over here it becomes A is 0. Okay, I'm gonna do the same for B. So 0, 1, 0, 1. So it becomes here 1, 0, 1, 0. So once I have this two, then I can compute the output over here. The output is just A bar or with B bar. So you have over here A bar already. You're just gonna OR these two together. So 1 and 1, 1 or 0, 1 also, 0 or 0, get the 0. Okay, so what I want to highlight over here is that the output over here is equal to this output. Okay, take a look at the output. The output here is 1110 for this value. The output over here is also 1110 for the same input value. So because the truth table essentially is the same, then we can say that this gate is equivalent to this gate. Okay, understand what I'm trying to say over here? We can say that system A is equal to system B if the truth table, they are the same. Okay, the truth table, they are the same. All right, now we can see that the expression here is not the same. We'll take a look in the next chapter why is the expression not the same and how can you get the same expression. But for this chapter, I would like you to see that when the two truth table, they are the same, then the two systems are considered to be equivalent. And in this case, NAND gate, so that's why I've written here, NAND gate is equivalent in operation with a negative OR gate. Okay, so that is how we check whether these two systems are equivalent. So clear on this, right? Right. So let's take a look at NOR gate now. So NOR gate, okay, this is again, it's a combination with OR gate with a NOT gate, and this is how it is combined, and this is how it is drawn. Okay, it's an OR gate with a bubble in front. All right. So this is also another hot cake. This is like you have a NAND gate and then you have a partner. The partner is like OR gate. So these are the two competing partner. So these are the two very popular gates because the NOR gate is also a universal gate. Okay, it's also a universal gate because using NOR gates, we can build any other gates. We can build any system with just the NOR gate. Okay, so that's why it's popular. Right, this is the Boolean expression for the NOR gate. So just take a quick look at this to make sure that it makes sense. So A plus B, this is OR, and then over here is A plus B. This is OR, and then if you go through the NOT gate, the entire thing will be inverted like that. Okay, this is not the same as this. Okay, they're not the same. This is A. Okay, the top one here, A bar plus B bar, is not the same as this. Okay, don't get confused. In the previous slide, we saw this one, this equation. It is not like, it's not the same. Okay, so bear in mind where the bar, the position of the bar can make a big difference. Okay, this bar is just over the A and over the B, and it's not bar over the plus sign over here. This one can make a big difference. This bar over here is over the plus sign, so just bear in mind with this difference. Okay, it's not the same like with this one. Okay, that is the Boolean expression. Now let's take a look at the NOR gate truth table. Okay, truth table looks like this. I think it also makes sense. So the Boolean expression is just A plus B, and you put a bar. So we can do here A plus B, 0 plus 0, and then you invert it, you get a 1. Okay, everything else is 0 plus 1. That gives you 1, and then you invert it, you get a 0. Same thing over here, 0 plus 1, you get a 1. Invert it, you get a 0. And 1 plus 1, you get 1. And you invert it, you get a 0. Okay, so is the inverted version of the NAND gate. If you notice, like in the NAND gate, your output was like this, but this one is the other way around. Okay, all right. Now let's take a look at a property of the NAND gate, like we did just now for the. This is a property of a NOR gate, just like we did in the NAND gate just now. So remember just now the NAND gate. So the NAND gate was equivalent. This three lines is an equivalent sign, equivalent to a negative OR gate. Okay, remember that was what we did just now. Why is it equivalent? Because the truth table is the same. Okay, truth table is the same. Now we are going to see this property in the NOR gate as well. So in the NOR gate over here, now we're saying that the NOR gate is equivalent to a negative AND gate. Okay, we're going to do the same thing like what we did just now. So let's take a look at it. So this is a NOR gate, and this is a Boolean expression, Boolean equation for a NOR gate. And over here, I have a negative AND gate. So negative AND gate, it helps you to understand. You can redraw it this way: negative, negative, and this is a AND gate. Okay, I believe you are a better artist than I do, so I think you can draw this better than me. All right, so this is A and B. Okay, over here, after going through the NOT gate, is A bar. So going through the NOT gate is B bar. Then over here is A bar. A bar multiply with B bar. Okay, or you can write it like this. The multiplication sign is sometimes not written down. Okay, right. Now with this in mind, now let's take a look at how the truth table of this guy and this guy, they are the same. So the truth table of NOR gate we have seen in the last slide just now, it looks like this. Now the truth table for this negative n, it's also very simple. So we can just construct the truth table very quickly over here. So we can say A, B. Okay. 0, 0, 0, 1, 1, 0, 1. Okay, and we need to have an A bar and B bar. So let's just try to do that. A bar, B bar. Okay, and then finally we can have the output. The output is output would be A bar, B bar, like so. Okay, let's take a look at how do we compute A bar. A bar is just an inversion of A. So A is 0011. The inversion of that will be 1, 1, O, O, then a B bar. So the B bar will be 1, O, 1, O. Okay, double check my work with me. O1, O1, O becomes 1, 1 becomes O, O becomes 1, 1 becomes O. Sometimes it's easy to mix up when you have so many 1, O, 1, O. Okay. Now, the output would be 1. All you got to do is just multiply these two together. You have A bar and B bar already here. So multiply 1, 1 is 1, 1 and O. Multiply together is, they're all zeros. Okay. So what I want you to notice is that the output, the truth table over here, essentially they are the same. Okay, for this input 00011, it produces this set of output. The same thing over here, we can see that for this combination of input, it produces this set of output. Okay, so what we can see over here is this two truth table, they are the same. So that's why we say that this NOT gate is equivalent in operation with a negative AND gate. So I want you guys to keep this property in mind, because in the next class, we are going to make good use of this property. Okay, so far so good, right? Any questions before we move on?
No, sir.
Okay. All right, next, we are going to take a look at another gate, which is the XOR gate. Okay, or this gate is also known as the exclusive OR gate. This is how it is drawn. So you can see that this is actually an OR gate, and then you have like a strange looking like curve in front of that. Okay, so this gate actually can be constructed with multiple AND gates and multiple OR gates. So inside of this, there's actually a multiple AND and multiple OR. So I'll show you guys. I think in the next class we can deconstruct this into simpler gates. But for now, I would like to show that this is how it works. Exclusive OR gate. Yeah, this is how it works. This is the Boolean expression of the exclusive OR gate. And as you can see already over here, the exclusive OR gate, the operation is like so. Okay, so we will take A and B, and we will perform this special operation. It's called the exclusive OR operation. So what is the exclusive OR operation? Actually, it can be broken down into this. Exclusive OR operation is just this. Okay, so you can take A and invert the B, and you add with the inverted A and B. That is what it means with the exclusive OR operation. So as you can see over here already, this operation is basically just using NOT gate, using OR gate, and using AND gate. Can you see what I see? Okay, we have a bar over here. This bar is going to use a NOT gate, right? We have an addition over here. This addition over here is obviously going to require OR gate. And we also have multiplication over here. For example, here is a multiplication, and here is another multiplication. It's an AND gate. So what it means over here is that to construct the exclusive OR gate, we are making use of these three gates. And if you really draw this out, you would end up with something like, you can draw, I believe you can draw this out yourself, right? So A AND gate, B with a NOT gate on top, and then you can wire it out with a OR gate, and then you do the reverse of that. Okay, so that is exclusive OR gate. So how it works? So this is how it works inside. So this is the truth table of a XOR gate. So if you look at this, so 0, 0 will give you a 0, and 1, 1 will also give you a 0. So the only time when it is a 1 is that when they are different. When they are different, then you get a 1. When they're the same, you get a 0. Okay. So to make sense of this, like maybe like some of you don't want to remember this. Okay, so you can actually break this down because the output is just A, B. Okay, remember what we saw here? Okay, A, B bar plus A bar B. So you can do that as well over here. So we can see that the output over here is A bar. You can do A bar, which is 1. And then like, okay, you can compute this output column by using the values over here, right? So we have over here A bar, which is 1. And then, so 1 and 0, that's 0. Then you OR with this 0 with 1. Okay, that gives you a 0. Okay, and you can do the same, and you would end up with exactly the same column as this. Okay, so this is how if you don't think you want to remember, then you can always compute. You can always make this table out by using this equation with just the basic logic gates. Okay, you should get a 1, 1, 0 like that. Okay, this is the XOR gate. Simple. And the last gate, I think, for today would be the exclusive NOR gate. Okay, just now we have an exclusive OR gate, and now we have an exclusive NOR gate. So the only difference would be this dot that we have in front over here. So the operation would be the same, except that it is an exclusive OR gate, but okay, draw this nicely so that I don't confuse myself with this is an exclusive OR gate, and then you put it through a NOT gate in front. So this is the exclusive NOR gate or XNOR gate. Okay, so if you're in a lab, that you will come across this gate as well. So the way we draw it is like this, just by putting this bubble in front. And the operation would be almost the same. It's just with a NOT gate in front. Previously, we saw that the XOR gate has this as the output. And now what we do is just put a bar over the entire thing. So that's how we arrive over here. Okay, so what about this guy? So remember, I can break this down into like this big bar, and then like everything inside here is just whatever that we saw in the XOR gate. Okay, that's how I got this one. Right, and this one will be the truth table. So you have 0, 0, so 1, 1, 0, 1, 1. And this will be just the inverted version. For just now, in the XOR gate, the only time that will be 1 is when they are different. But in this case, the only time that will be 1 is when they are the same, which is this case and this case. Okay, XNOR gate likes to be the same. XOR gate likes to be different. Okay, that's how I remember it. First, you can also construct this output column by using the equation just now. We have A, B, okay, like so. And you should get this as the output if you do this. So you should get 0, 0, 1 as well. Okay, so that is all for the advanced logic gates. So I believe that by now you should be able to understand what is the difference between basic logic gates and advanced logic gates, and how they operate, and how to describe their operation. Okay, remember the 3 things: truth table, Boolean expression, and what's one more? Timing diagram, right? Okay, so for any system, you can try to do these 3 things. And now let's take a look at some exercise over here. So we can also produce the truth table for this. Now, it's the same like the last exercise we did in the class just in our last class, but this time we have this advanced logic gate over here. All right, so let's try and attempt to do this one. So take a look what we have over here. We have the input to the system, and then we have the output to the system. So when I say a system, so a system means that you can imagine this to be a box over here, and this box can contain any number of logic gates. Okay, in this case we are lucky because this got only like 2 logic gates over here. So this is a system, and the input to the system is usually on the left, and the output of the system is usually on the right. So what we want to do is to produce the truth table over here. So what we can do is we can try to list down what are the possible input combination, and also this time we have multiple outputs. So in all other previous example, our outputs, we only have one output, right? But in a real world system, you have many outputs. Like, it's not only one output. Okay, so in this example over here, we are seeing over here we have output number 1 is S, and output number 2 is C. Okay, you can call it any other letters that you want, but I'm gonna stick with this S and C. All right. So what are the possible combination of inputs? So for A and B, as it is as usual, we can start with 0, 0, and then we can go to 0, 1, and we go to 1, 0, and we can go to 1, 1. Okay, so now let's try to produce the output for this. Okay. Okay, so let's try. There is like multiple ways for you to do it. You can use the manual simulation mode, which means that you can input the 0, 0 value, and then you can try to get the output. And you can also do the Boolean expression mode. Okay, so I'm gonna do the Boolean expression method. All right. So we see over here that the output C is coming from this A, B. So here we have A, B. Okay, the output S is also coming from A and B. Okay, so what is the output S? So the output S is, I'm gonna write this equation over here, A XOR B. A XOR B. Okay, so the output carry C is just A multiplied with B. Just A multiplied with B. Okay, now since we already have this master key over here, we already have the output equation. Now we can really easily plug this into our truth table. Now for the first one, let's look at the sum, not the sum, the S. Okay, right? So A XOR B. So let's take a look at what is A XOR B. Remember for the truth table for XOR. So the truth table for XOR. So XOR likes to be different. When it's different, then it gives you a high signal. Okay, when it's the same, it gives you a low signal. With that, let's try to solve this. Okay, so when it's the same, it gives you a low signal. Okay, logic low. When it's different over here, it gives you a high. No, and it's the same, it gives you the low signal. Okay, that is basically S. Okay, what about C? C is very straightforward because it's just n multiplication over here. So which means we can take A multiplied by B. 0, 0, 0, 1. Okay, there you go. That is how easy it is to fill in the truth table of a system. Okay, you can do this for any system you like. You can be a complicated system, but as long as you get this Boolean expression, you can fill in this quite quickly. All right, so what we did over here is a simple calculator, believe it or not. Believe it or not, this is actually a simple calculator. All right, so why do I say it's a simple calculator? Okay, there's a reason why. If you take a look at this first row, what it's doing over here is actually addition, and S stands for sum. That's why I use this letter S over here, and C stands for carry. Okay, so just take a look over here. 0, A and B 0, 0. What this calculator is doing is taking this 0 and it's taking this value. They add them together, and that produces the sum. Okay, so in this case, it's 0 plus 0. Of course, you get the sum to be 0 and carry also 0 because like 0 plus 0, there is nothing, and there's also no carry. Okay, so 0 plus 1. So 0 plus 1, it's supposed to produce a sum of 1. Okay, but there's no carry. So which is what we see over here. Sum is 1, there's no carry. So 1, 0, same thing. The sum needs to be 1, and then the carry is 0, and 1, 1. So 1 plus 1, as we've seen in the last in our last class. So 1 and 1 plus 1, you get a 0 to be the answer, but then you have a carry. So that is what we expect over here, carry and 0 sum. Okay, so this system is a very simple calculator that can do addition. Okay? It can do addition. All right, so that is how we design systems. So you design system by making the truth table, and then from the truth table we see how we arrange how can we arrange this logic gate that can produce this truth table. Okay, we'll see that in detail in the next chapter on how we construct any system at all. Okay, but for now, just bear in mind that this relatively simple combination of logic gate is actually a calculator that does addition. All right, so any questions so far with this example?
No, sir.
No question? Okay. Okay, so if no question, then this will be the last slide for this topic. And this topic is the first time I am going to introduce to you guys a video assignment. So this is the next video assignment. If you notice, like this week, I haven't been giving you any quizzes in the class because I'm preparing this video assignment for you guys. Okay, so this video assignment, yes, it requires you to make a video. All right, so let's just go through quickly on how this assignment is structured. So it's called video assignment 3 is because this is for topic 3, okay? It's not the assignment number 3. This is for topic 3, topic number. Okay, there's no video assignment 1, there's no video assignment 2, okay? This is our video assignment 3 for topic 3. All right, so this is the question. With the knowledge that you have learned in logic gates, think of a problem in your daily life that you can solve using at least 3 logic gates. Okay, 3 logic gates. So you can think the problems that I covered in the class, that you remember, the problems of the floodgates, the problems of the car opening the door and closing the door. These are very, very simple problems. I believe that in your life, you also have this kind of problem that you can easily solve using logic gates. Okay, you can use my minimum requirement is use at least 3 logic gates to solve this problem. Okay, now here's where things get interesting. So we are going to use software, online software. These are simulator software at logic.ly or circuitverse.org. You can choose whichever you like, and then you can actually simulate your gates over there, right? And when you got the gates working, now I need you to record like maximum 5 minutes video showing like yourself, like your face has got to be visible, like what I'm doing with you right now. And the video maximum is just 5 minutes, don't go more than that. And you present your solution. Okay, you present your solution and what are you trying to solve. You mention what you're trying to solve, and this is the logic gates. And then also like you got to show me the 3 things that 3 elements that we have learned in the class. So which is the truth table, timing diagram, and then the Boolean expression. Okay, so the solution needs to have these 3 elements in the video. Okay, all right, and once you're done with the video, I need you to put it on YouTube. Okay, post it on YouTube, and then send the link to me. Okay, I will post a form that allows you to paste this YouTube link. Okay, to those of you who think that, oh, am I making myself visible to the world? No, because if you think that you don't want to make your solution to the rest of the world, like make known to the rest of the world, you can make use of this unlisted feature on YouTube. Unlisted means that your video will not appear on anybody's search result. So the only way that a person can view the video is that if you send them the link. Okay, if you share a link, then the person can view. So this is the link that you will share to me. If you choose to go unlisted with your video, of course, you can make your video public. There's no issues with that also. All right, so put it on YouTube and you can make it unlisted if you want. And the video link submission will be on Teams. And the deadline will be in 1 week. Okay, 1 week from now, that is. All right, so I'll go through a little bit on how do you make this recording. So I will highly recommend you to use this tool. It's called OBS. This is a free tool that you can install on your computer. You can just search for this Open Broadcaster software. Okay, FT. Okay, so okay, you know what? Let me just show you right now how do you do that, and so that you can. So any question on this first before I show you a demo on how to do this? Okay, so think of a problem, use 3 logic gates and use a simulator, and you need to cover these three elements: timing diagram, truth table, and Boolean expression. Okay, no questions. All right, then let's just look at how we do this. Okay, let me share my screen over here. Okay, so if you go to Google, you can Google Open Broadcaster software. Okay, so this is a software that I encourage you to download to do the screen recording. Okay, you can open this and you can, I'll post some tutorials also how to use this. Okay, let's say in the event that, oh, I don't want to learn this new software, it's kind of, it's kind of hassle. Okay, you can also use Teams to do the recording if you want. Okay, so you go you go onto your Teams and then you create a video chat, and then you join the video chat yourself. And then in the video chat, you can share your screen, and then your face will be visible, and then you can record the entire session yourself. So that is another way of doing things if you like. Okay, but if you feel like that is not good, like, I will highly encourage you guys to learn this, because I think this is a very useful tool for anyone to learn OBS. Okay. All right. The other thing is that we can go to Circuitverse. Once you've got your logic gate done, you can go to Circuitverse, or you can go to logic.ly. So any one of this works. Okay, I prefer Circuitverse because it's 100% free. There's no charge or anything. Logically is also free, but you got to do the trial version to get the free version. Okay, so let's just go through how to use this. If you go to Circuitverse, you can launch a simulator, and then in this simulator, you would get a few elements. Okay, there's input element, there's output element, and see, there's also gates. So these are all the gates that you can play around with. Okay, let's start with the simplest of all. I'm going to zoom in. I have this gate, NOT gate, and I have the output. So I'm gonna select this digital LED, so this as my output device, and I'm gonna select an input device. So this is my input. This is something that I can control, input, and I'm gonna wire them up together like so. Okay, so what happens if I change the input value? So you know that if you give a value of 1 and it goes to NOT gate, it becomes a 0, right? So which makes sense. But what happens if I flip this? So look at that. If I flip this 0 and it goes to this NOT gate, it becomes a 1, and then this 1 makes your LED to light up. So just by using this alone, that you can make multiple examples. Okay, you can make multiple gates to work together. Okay, for example, you can also combine this gate to be like so. Okay, so you can remove this, delete this, and Okay, the output, I'm still gonna put the output over here. Okay, and I'm gonna say the input, another input over here. The output is going to come from here. And this is going to be connected like so. Okay, so you can see if you change this, what happens. Okay, and you can verify this behavior with a truth table. Okay, so if you have 0, 0, the truth table, what's the truth table? And then you have 0, 1, what's the truth table? And you have 1, 0, what's the truth table? And you have 1, 1, what's the truth table? And the truth table should correspond to what you are seeing over here. Okay, right. You can also put in annotation. You can also put in text over here. Make things more tidy. Wait, text rectangle. Okay, you can explore this yourself. Rectangle. Okay, you can put a rectangle to denote the system. Okay, let me delete that. Put a text. How do I change this text? Oh, okay, it's here. So we can put here text to be A. So we can put here to denote that this is A. And you can put in the text over here that say this is B. This is B. And you can put in a text over here, and you can just to label this as maybe X. Okay, so then when you have labels like this, then when you show your truth table, then it's easy to point. Okay, this truth table corresponds to A and B, is the input, and X is the output, right? So you have other complicated elements as well, which we will not touch right now. We will be touching them in the next in the future class, but you can make use of this tree. There's gates, there is outputs, and there is inputs. Okay. All right. So there is yeah, I think yeah, you can make use of this button as well. So button functions like that. You wire them like that. So okay, it's not working. Bit width. Okay. I'm not too sure right now how this button works. I haven't tried button myself yet, but I think it's something that you can explore. Button. Okay, so if you can use that, please feel free to go forward. I'm also going to explore this too myself. Any question on this one? Circuit bus. So you can actually generate a timing diagram from this over here, but I leave that to you to explore. If you're not too sure how to generate this, you can always make the timing diagram yourself. Okay. That is circuit verse, and now I'm going to show you logically. Okay, for logic, you can try this on the browser, and it works the same way, but I think the interface is slightly different. So you also have this NOT gate. So NOT gate, and you have this, yeah, this one is the push button. You have this something called toggle switch, and you also have this push button, and then you also have this output. I'm gonna put a light bulb here. Okay. Okay, this toggle switch is going to change the state when it's 1 and it's 0. When it's okay, so this is just going to invert the state. So you can construct the any logic combination as well. So delete this. How do we delete this? Delete. You can construct this the same circuit like what we did, and then we can have a toggle switch. Okay, so if this is high, this is low. Okay, so when it is high, you will see that this line becomes blue. Okay. Right, so you have also other elements. You have other gates. So I believe that you're familiar with most of the gates over here: NOT gate, AND gate, NAND gate, OR gate, NOR, XOR, XNOR. Okay, so there are other form of gates that we will not cover in the class also. All right, so that is all. So I really hope that this video, you can make it as interesting as possible. I'm looking forward to seeing your videos. Any question before we end our class?
So once after we do the simulation, we have to upload in YouTube, right?
You do the simulation, you record the video with showing you like presenting and show in that video, and then you upload it to YouTube, and then you get the link, and then you submit the link into the Teams. I will prepare a form for you to submit the link.
Oh, okay, sir. So the due date is next week, Thursday, is it?
Yes, exactly on this day, next week.
Okay.
Okay, any other question? Okay, so anyone wants to speak? Okay, if there is no question, so for those of you who are wondering if I'm going to discuss the quiz, like yesterday we accidentally discussed the quiz, the last question on the BCD edition. So the session was recorded yesterday. So those of you who left earlier, you can view the session recording. So I'm just gonna see what else. Is there anything to discuss on the quiz? Let me just go back to the quiz. Is 2.2.2, I believe. Okay, so I am just briefly going to go through what we did in the last quiz. So in the last quiz, this is just converting. The first question was converting unsigned binary number into a decimal equivalent, and using whatever method, right? So it's 5 points each. So one-way conversion. So some of you, I noticed that you do the one conversion from this number binary to decimal, but you didn't reverse the conversion. So that is one potential error over there. So I think most of you got this one right. And this one is the same thing as well. You can convert this by using the shortcut method. So the other thing with the shortcut method is I noticed that some of you are using the shortcut method to convert into decimal. Okay, remember the shortcut method does not apply to decimal. It is only applicable when you have base 2 to base 8, base 2 to base 16, or the other way around. Okay, that you can use the shortcut method. And question 3 and question 4 is depending on your ID number. So question 3 is that you're required to add all the digits in your ID number. So like example over here is if your ID is like that, 1, 2, 3, 4, 5, 6, you can add them over here like that. And then your answer must be in an unsigned binary format. So there's actually two ways of doing this. You can add them in decimal and then convert them. That's one way of doing it. But you can also convert them to binary first, and then you add them in binary, and that should give you the same answer. So whichever method you use, you should produce the same result of the addition. Okay. And the last one is subtraction. So let's say you have your ID is EP something something, and then you're supposed to take the digit 999999, and then you subtract from your ID. So some of you also message me, what if my ID is not 6 digits? So of course you can always add one more digit to your 999999. Okay, if your ID is more than this, then you can add one more digit to this 9 over here to do the subtraction. Okay. But I also considered like the case because it's not very clear, and then the deadline has already passed. So I also considered that if you didn't do, as long as you do the subtraction, then marks will be given to you. Okay, that is a case by case basis. I will inspect your workings instead of focusing on this minor details. Okay, so that is how I will grade. If you think that you deserve more marks, then please get back to me. Okay, so that is all that I am going to talk about with the quiz. Do we have another quiz? Where's the BCD quiz? Okay, so for the BCD quiz, I haven't returned your results. Okay, so let's discuss this quiz, the BCD quiz, after you've gotten your results. So I'm gonna mark this today, and then let's discuss this in next class. Okay. All right. So I think that is all from me today. I will end my class over here. Let me share my presentation slides again over here. If you have not signed in your attendance earlier on, this is the attendance QR code. If there is nothing more, then thank you very much. I will see you guys again in the next class. Take care, everybody.
Thank you, sir. Thank you, sir.
Bye-bye.
Thank you, sir.
Thank you, sir.
Right, you're welcome.
Thank you, sir.